and string theory. So when you want.
Great, thank you. In the last two lectures, we reviewed properties of the TTbar operator, and in particular, we learned about the differences between the single and double trace versions of TTbar. And we also reviewed some basic aspects of string theory and ADS3. So now we're finally ready to come back to the question that we asked in the first lecture, which is given holographic duality between some conformal field theory and string theory and ADS3, what is the holographic dual of doing the TTbar deformation on the CFT side? As we saw last time at k equals 1, string theory and ADS3 is holographically dual to a symmetric orbifold. So in that case, we can ask what's the holographic dual to the single or double trace versions of the TTbar operator. For any other value of k, it turns out that the single trace deformation of the long string sector of string theory is more natural. And we're going to see why this is the case. Okay, so in this lecture, I'm going to consider, on the first part of this lecture, I'm going to consider the massless BTC black hole for simplicity. This is given by this metric, and I'm choosing a different gauge from the previous lecture for convenience, and to relate the two, you can use this formula. And this background is going to be supported again by a B field that is given in this way. And as before, I'm ignoring other parts of the background, like the sphere and the T4. The nether currents on this background are chiral, as we mentioned last time, and agree with the currents of the with the Wessel-Minowitten currents. So, for example, for translations which are generated by this Killing vector, the nether current GDU agrees with the Wessel-Minowitten current and is given by this expression here. And similarly, for the Killing vector that generates chiral dilations, you find the corresponding nether current. And for the other Killing vector that forms part of the SL2R algebra, which generates a chiral version of special conformal transformations, you find some other nether current. And as an exercise, you can try to find what these other nether currents are and verify that they're indeed chirally conserved. So why have I written these currents here? It's because we can use them to construct a vertex operator, which is to say an operator of dimension 1,1 on the worldsheet that corresponds to the stress tensor of the dual CFT. So this is really special, something that happens for string theory in ADS3 with only NS flux. And the ingredients that we need in order to show this are the following. First, we're going to need the representation of the SL2R algebra on the dual CFT. So this is going to be given by these currents. This one generates translations. So we're going to use X and X bar to denote auxiliary coordinates on the dual CFT. Similarly, we have the generator of chiral scale transformations. Here, H is the conformal weight from the perspective of the dual CFT. And we have this other generator of special conformal transformations. The second ingredient we're going to need is the set of primary fields. And these are primary fields which are representations of both SL2R algebras, meaning the one that we find in the worldsheet and the one that we find on the boundary side, on the dual CFT. So in particular, they satisfy the following equation, where here, this is the Lie derivative with respect to the Killing vectors that I had written before. So in particular, we can check that the Casimir acting on this primary field phi h is just given by 1/4 box of phi h, from which we can read the mass of this field in ADS. So the mass is simply given by this formula, which you can recognize as the standard formula that relates the mass and the conformal weight in the ADS-CFD correspondence. Something else that we will need to know about these primary fields are their conformal weights. So with respect to the symmetry algebra of the dual CFD, the conformal weights are given by H and H, whereas with respect to the worldsheet algebra, they're given by delta, where delta is given in this way. Okay? And the last ingredient that we need to construct this vertex operator that corresponds to the stress tensor is the so-called soldering current, which glues the coordinates, the auxiliary coordinates of the CFD at the boundary and the worldsheet coordinates in this way. And what's interesting about this, something that is interesting about this current is that it has appeared before. So it appeared in a paper by Polyakov when he was trying to quantize gravity in the following gauge, something like this. These currents appear there. And the reason was that the theory had some SL2R symmetry. So what's important about these currents, or something that we will use about these currents, is that they satisfy the following equation. And in particular, if you take two derivatives with respect to x, you just get this J minus current. And I think with a minus sign. And some factors of 2. Okay. And the conformal weights of this current are given as follows. So on the dual CFD, we have a weight minus 1,0 that you can just check. And from the worldsheet, we have weight 1,0 because the auxiliary coordinates do not carry any weight from the perspective of the worldsheet CFD. So using the scaling dimensions of these objects, we can construct a vertex operator that has the dimensions of the stress energy tensor in the dual CFD, namely conformal weight 2,0. And this stress energy tensor, or rather this candidate stress energy tensor, contains a combination of these terms. And we can check that all of these terms have the proper dimensions. So let me focus, for example, on the third one here. So with respect to the worldsheet, theory, this term here carries no dimensions because these are just some auxiliary coordinates. J, as we saw, has dimension 1,0. Phi 1 has dimension 0,0. So here, this is phi h from before, where h has been set to 1. And J bar has dimension 0,1. So altogether, this is indeed a vertex operator with dimension 1,1. And from the point of view of the dual CFD, we can similarly see that this has dimension 2,0. This one has dimension minus 1,0, 1,1, and 0, minus 1. And indeed, its CFD dimension is just 2,0, which is appropriate for a stress energy tensor. Now, the coefficients AI here that have been left free can be fixed by imposing the physical state conditions on this operator or requiring that it transforms like the stress energy tensor. So what you find at the end of the day is that this object is given as follows. Okay. And it meets all of the properties that we expect from the stress energy tensor of the dual CFD. In particular, it satisfies the TT OPE. And so I'm going to show you how this calculation is done, but not without giving you too many details. So the strategy to evaluate this OPE and other similar OPEs that we will encounter later on is to use the following identity. So the derivative with respect to x bar of this combination turns out to be equal to a derivative with respect to z bar of just phi 1. Okay, so this means that if I act with the derivative with respect to x bar of t, I get this expression on the right-hand side. This thing is not zero, as you might expect, but it turns out to be zero when you insert it in correlation functions up to some contact terms. And the important thing to notice about this expression is that unlike the stress energy tensor that appears up here, where we integrate over both sets of worldsheet coordinates, here we just have a contour integral. Okay, so the strategy to evaluate the correlator is to consider first this OPE that you see on the left-hand side. There are many terms. I have only considered one of the terms that appears on the right-hand side. And you see, we indeed have just one contour integral. So what we're going to do is we do all possible big contractions, and then this integral will pick up the poles. So for example, there will be poles coming from this contraction, as well as poles coming from this contraction. So at the end of the day, you evaluate the contour integral, which is going to set z, the worldsheet coordinate z, to be equal to the worldsheet coordinate w, and you'll end up with an expression of this form. And the important thing to note about this expression is that we can turn this delta function into a derivative with respect to x, the x bar of 1 over x minus y. So at the end of the day, the left-hand side here, the left-hand side here is going to contain a derivative with respect to x bar, and the right-hand side here is also going to contain a derivative with respect to x bar. So you can extract the TOPE from this expression up to some regular terms that are ignored when you write down the OPEs. So what's the result that we get? We get, as expected, the OPE for a stress energy tensor, where the important thing to notice here is that the central term, so the central charge here, is 6 kP. And if you remember from the previous lecture, this is what you expect from the holographic dictionary. Okay. What else can we say here is that this equation, the fact that this current vanishes, implies that there are no other chiral vertex operators with weight h greater than 2 other than derivatives of the stress tensor. So if we're interested in chiral vertex operators, this is it. We have the stress energy tensor. But if we are not interested in chiral vertex operators, there's something else we can construct, and it's an operator with dimension 2,2. So the same quantum numbers that you expect from the TTbar operator. Okay, so this operator turns out to be given by this expression. And the important thing to notice here is that there's a component that looks, that comes from T, basically, that is also featured in the definition of T, and a piece that comes from T bar. And you can check that the conformal weights with respect to the dual CFD of this piece is 1,0, this one is 0,1, and again, this one has 1,1. So indeed, this looks naively like an operator of dimension 2,2. Of course, in order to verify this, you need to compute the OPE with respect to the stress energy tensor, and you can use the same trick that I told you before in this context, and what you find is the following OPE. So indeed, you see there's a factor of 2 here, as you would expect. There's a similar OPE with the T-bar component of the stress energy tensor. And the other important thing to notice here is the central charge. So the central extension here is only 6K instead of 6 kP, instead of being the central charge of the full theory. And in order to understand this difference, it's helpful to go back to the double and single trace versions of the TTbar operator in a symmetric orbifold, whose seed central charge is just 6K. And we're going to evaluate the OPEs of these operators with the stress tensor and see what we get. So the OPE of the stress tensor with the double trace TTbar operator, so remember it's double trace, there are these two sums here, is given as follows. So we have 3 sums for different copies of the stress energy tensor. And because the stress energy tensors on different copies of the symmetric orbifold don't talk to each other, and we get a Kronecker delta from here, So on the right-hand side, we end up with only two sums and this expression. And you can rewrite this in terms of the TTbar operator, as you can see here. And the special thing to notice is, again, what central charge appears here. So the central charge that appears here is the full central charge of the symmetric orbifold 6 kp. And now we can repeat the same exercise for the single trace version of this operator. And what we get in this case is just two sums on this side. We again get, sorry, this should be just two sums. We again get Kronecker delta here. So the right-hand side here that contains only one sum. And at the end of the day, the central extension that you get is just the central extension of the seed theory, 6K. So what this means, so this is exactly the same OPE that we found up here for the stress energy tensor with respect to this operator D. So what this means is that this operator corresponds to the vertex operator for a single trace version of TTbar instead of the double trace version. And in fact, this is the only operator of dimension 2,2 that you can find on the worldsheet. There are no other local vertex operators with this conformal weight. And if you try to do it, say if you try to construct the double trace version of TTbar, you're going to end up with an operator that, from the worldsheet point of view, is non-local and given by an expression that looks like this. Okay, so now that we have this operator, which has the same quantum numbers as single trace TTbar, we're going to consider deforming the worldsheet action by this operator. So we're going to consider a deformation of this form. So here I should use a squiggly line because we have not established that it's exactly the same. And what we get on the right-hand side is an expression like this. All I have done on the right-hand side is move total derivatives around and thrown total derivative terms to get a simple expression like what you can see. And the interesting thing about this expression is that, as we saw before, this is proportional to J minus. This was the current on the worldsheet that generates translations along U. This is proportional to J bar minus, which generates translations along V. And so the only X dependence of this object lies on this term, which is a constant. Okay. So what this means is that this single trace TTbar deformation reduces on the worldsheet to something that looks like a current deformation, J minus C, J bar minus C. Okay. And this, it's a very important equation, so I'm going to put it in this box. And now let me make a few comments about why this is so important. So the first comment I want to make is that remember that translations along this U coordinate on the worldsheets on the bulk side are generated by the nether currents J du, J partial U, which is the same for the massless BTC black hole as the J minus current. On the other hand, the current that generates translations along X in the dual CFT, so X and U are identified by the holographic dictionary, is just T of X. And so there's a very precise sense in which this deformation that I have written up here, namely this J du, J dV deformation, looks like a TTbar deformation because it's made of currents that generate the same transformations as T and T bar. The second remarkable thing about this equation up here is that the deformation is exactly marginal on the worldsheet. Okay, in particular, it preserves the shift symmetry or translations along U, the U and V coordinates. Because this deformation is exactly marginal, it preserves the conformal symmetry of the worldsheet. So if we deform the theory by this operator, it just moves us along the conformal manifold. Another way to say this is that this deformation is going to generate a new solution to the supergravity equations of motion. So these are some very nice features of this deformation by this operator D, but there are some drawbacks. And one of the drawbacks is that this operator is not known away from the CFT fixed point. But this is easy to solve because we don't need to work with this operator. We can just work with the currents, J minus and J bar minus. But then another problem is that these currents are not chiral for other ADS3 backgrounds. And this is something we saw in the previous lecture that say for global ADS, they were not chiral, and they were not chiral for the BTC background either. What we must do now is we must generalize this current deformation to something that can be applied to more general settings. And in order to motivate what the generalization is, I'm going to first rewrite the TTbar deformation in terms of the currents generating translations. So what I mean by this is that I can write the following current in terms of the stress energy tensor. And I can also define the following current. I have used quotation marks here for currents because these are, of course, not really currents, and they don't transform appropriately in their, say, coordinate transformations. But nevertheless, you can check that they are conserved as you expect. And now I can write the TTbar deformation that we saw before in terms of these variables. So that in terms of these variables, the TTbar deformation takes this simple form. And something I can say about this is that this expression can be easily generalized to other deformations, for example, to JT bar. Okay. So now, inspired by this equation and also by the fact that we learned up here, namely that this single trace deformation becomes a current deformation on the worldsheet. The proposal is that what the single trace version of TTbar corresponds on the worldsheet is given by the following differential equation, where we deform the worldsheet action by this set of currents, where these are the nether currents from the worldsheet point of view, and they're also instantaneous. Which means that they are the currents of the theory that has already been deformed. And in particular, the holographic dictionary between this deformation parameter and the one that appears in the TTbar, the definition of the TTbar deformation is just obtained by putting the scale of ADS so that we get the right dimensions. Okay. When written in this way, it turns out that the deformation is also exactly marginal. And one way to see this is that you can perform a change of coordinates, which from the context of the worldsheet nonlinear sigma model is just a field redefinition to put this into a current type of deformation. Okay. So now that we have this differential equation, our goal is going to be to look at its solutions. And the first step to find the solutions to this differential equation is going to be to write the action and the nether currents in terms of matrix variables, because this makes things a bit simpler. So for example, I can write the worldsheet action in this way, where this is now a vector. So d bar x is a vector. It contains derivatives with respect to all the worldsheet all the target space coordinates in this way. And M is as before, remember, just made it's made up of the background fields. And similarly, I can write the nether current in matrix notation in this way. So now if I plug these formulas into the differential equation for the action, I get another differential equation for the background field M that looks like this, where this gamma here is an antisymmetric matrix that is defined in this way. So the alpha beta components of the matrix are defined this way, which is to say, if you parameterize the matrix in this way, there's going to be a 1 here, a -1, and everything else is 0. Okay. Now, if this was not a matrix equation, it would be very easy to solve. It turns out that as a matrix equation, it's also still easy to solve. And the trick to solve it is to write the differential equation for M inverse instead of M. And then the solution is simply given by this expression, where now this M of mu, M of mu is the deformed background, and M of 0 is the original ADS3 background that we started with. Okay. So now we may ask, what does this correspond to in string theory? And it turns out that this is known. And the answer is that it corresponds to a so-called Tsc transformation, where T refers to a T-duality along U. S is a shift of coordinates, where V goes to V minus mu hat U. And T is another T-duality along U that takes us back to the original frame. Now, a Tsc transformation is known to be exactly marginal to one loop, provided that the dilaton transforms appropriately. So the dilaton transforms in this way, and this transformation is known as Buscher's rule. So here, G tilde and phi tilde are the transform values of the field. But in our context, it turns out that we're going to need to add an additional constant, which doesn't spoil the equations of motion. You can always add it, and it turns out to be important, as we will see soon enough. In other words, the fact that this TSC transformation is exactly marginal to one loop is just telling us that TST is a solution generating technique of supergravity. It's going to give us a new solution. And something to note about this new solution is that it satisfies it's going to generically satisfy different boundary conditions than the undeformed background, which means that TST changes the UV behavior of the dual theory, which is what we expect from an irrelevant deformation like TTbar or JTbar. And indeed, it turns out that you can perform these TST transformations for any background that has at least two isometries, two translational isometries. So for an ADS3 cross S3 cross T4 background, for example, we have the following interpretation. So if you take the TST coordinates from the ADS3 part of the background, say U and V, then the interpretation is that of a single trace TTbar deformation. You can also take just one coordinate from the ADS3 part, say U, and a coordinate from the internal manifold, for example, the T4, and this is interpreted as a TJ-bar deformation. And similarly, you can take a coordinate from V and another one from the internal manifold, say S3, in order to get a JT-bar deformation. And in fact, you can also perform a sequence of TSC transformations, and that would correspond to having a linear combination of these irrelevant deformations in the dual theory. Okay, so let me summarize what we have discussed so far. So we started by thinking of the holographic dual and the fact that string theory in ADS3 has a sector, the long string sector, which is described by a symmetric orbifold, and we can deform that symmetric orbifold by a single trace version of the TTbar operator or JT-bar or something else. Okay, and the statement here is that the holographic dual of this on the worldsheet theory corresponds to doing marginal deformation, and exactly marginal deformation that is driven by this J wedge J operator, which is defined, these are network currents on the worldsheet. And this deformation takes us from, on the worldsheet side, from an SL2R Wessel-Witten model. It takes us to another Wessel-Witten model, which turns out to be a gauged Wessel-Witten model. Okay, and an equivalent way to think about this is from the supergravity point of view. So from the supergravity point of view, this J wedge J transformation is a TST transformation on the space of solutions. So on the worldsheet, we're moving along the conformal manifold. On the supergravity side, we're moving on the space, along the space of solutions. And this TST transformation takes us from a locally ADS3 spacetime that we have called M of 0 to some other spacetime, which turns out to be for TTbar, a linear dilaton spacetime that we call M mu hat. Okay. So are there any questions about this picture? Okay, if not, then I'm going to use this picture to now study the kind of backgrounds that you get by performing this marginal deformation on the worldsheet, or equivalently, this TST transformation on the supergravity side. Okay, so what I'm going to do is I'm going to consider the TSC transformation that corresponds to TTbar, which is the subject of these lectures, where the TST coordinates are along U and V. So in other words, I'm going to take an ADS3 background, which is going to be the BTC black hole. So this is a 10-dimensional background, and this is going to yield after TST something that I will call a TST black hole times S3 times T4. So as before, I'm going to focus on the 3-dimensional part of the spacetime. And the TST black hole is described by this metric, where the only effect of the TSC transformation is on this, on the denominator here. And I have defined lambda in terms of mu hat in this way for convenience. And this background must be supported by a B field that is given in this way, and by a dilaton that looks like this. So remember that I told you that the dilaton was given by Buscher's rule up to some constant, and this constant is given here. And the reason that we need this constant is to preserve the electric and magnetic charges of the background. So remember in the previous lecture, we saw that these locally ADS3 backgrounds we were considering had electric and magnetic charges. And so in order to preserve this, we have to set e to the 2 phi naught to be equal to this value. Okay, so the space of solutions can be parameterized in this way. So the mass of these spacetimes takes the following form. This is the gravitational charge associated with this spacetime, where you can see the effect of the deformation here and here. And similarly, the angular momentum is given in this way. So all of the solutions that lie on this region here are these TST black holes. Down here in red, where the mass and angular momentum is 0, you find the massless version of the TST black hole, which is what you would obtain if you carried out the J bar minus deformation that we were discussing before. And the vacuum of, or the ground state of this space of solutions sits somewhere down here and is obtained by analytic continuation of the solutions that I presented to you, that I showed you before. And we'll discuss this soon enough. Okay, so what are the features? So there are many features that we can extract from this geometry without having to just by looking at the geometry. So let me tell you what they are. First, we know that asymptotic behavior has changed, and it has changed in a dramatic way, in the sense that before we had a divergence on this term as we went to infinity, but this is no longer the case. Similarly, the B field is finite at infinity, but now the dilaton, which used to be constant, now diverges. And in fact, one can compute the Ricci scalar in the Einstein frame, and one finds that after the deformation, it becomes proportional to -1 over r squared, which goes to 0 as you go to infinity. So the Ricci scalar is plotted here. So in the deep in the IR, where r goes to 0, you find the value of the Ricci scalar for just pure ADS, which is constant and negative. But as you move in the radial direction, and in particular, as you go to infinity, you see that the curvature becomes 0 and the spacetime becomes flat. What else can we say about this geometry? Well, we can set the deformation parameter to be negative, and then we discover some pathologies. So what are these? We find that there are going to be both closed time-like curves and a curvature singularity if the deformation parameter here becomes negative. And the location of these pathologies is given by this formula, which you see as lambda, when lambda is small, it scales like 1 over lambda. And this makes sense because as you turn off the deformation from the negative side, you take these CTCs and this curvature singularity, and you start pushing it away all the way to infinity until they disappear when lambda goes to 0. Okay, so that's all I wanted to say about the geometry, or no, maybe one last thing is the ground state geometry. So how do you get the ground state? You perform an analytic continuation of the solutions that I showed you before, where you require that the geometry is smooth everywhere. So what does this analytic continuation look like? I'm going to write it down here. So TU and TB are going to be equal to I over lambda, 1 minus square root 1 minus lambda. And the interesting thing about this analytic continuation is that it depends on the deformation parameter. And in particular, you can see here that the ground state, for the ground state to be real, only if lambda is less or equal than 1. Okay. And if you're interested to see how this comes about, you can do the following exercise. You can parameterize the temperatures or this TU TB parameter in this way and find the equation that are not mass satisfied so that you don't have any conical singularities in this geometry. And then you can find the solutions to this equation and show that they can be put into this form. And there are two, because there's a square root, you're going to get two solutions, and you can justify, you have to justify why we have to choose this one instead of the other one. So what we learn by just looking at the geometry is that a healthy space of solutions requires lambda to be greater or equal than 0, but also to be less or equal than 1. Why is this interesting? This is interesting because this is compatible with what we learned about the TTbar spectrum in the first lecture. So let us recall what we did back then. So remember that the spectrum of a seed TTbar deformed CFD in this symmetric orbifold is given by this formula. This is, you see there's the characteristic square root of the TTbar spectrum. And long ago, we learned that for large and deformed values of the energy becomes complex if mu was less than 0, okay? And similarly, we learned that for the ground state, the energies would also become complex if mu satisfied this bound. So in other words, just by looking at the spectrum, we learned that that the spectrum would be real if mu satisfied the following conditions, which, if you use the holographic dictionary, are equivalent to the same conditions that we find by requiring, a healthy geometry. So what does this mean? This means that we have a very strong hint that the TST solutions that we describe above are related to TTbar. And in fact, some of the details in this calculation of the spectrum depend on the single trace version of TTbar. So it has to be single trace TTbar. Okay, so I guess I have 5 more minutes. Yeah. Okay, so
yes.
Since I expected not to have too much time, I'm going to skip the derivation of the spectrum, and I'm just going to tell you that TST is very useful in deriving the spectrum. And at the end of the day, what we find is that the energies of the undeformed theory, so the energies before TST and the energies after TST look like this, where W was the winding parameter that we discussed in the previous lecture. And what this means is that the spectrum of strings on any TST transform background matches the spectrum of a single trace TTbar deformed CFD. Of course, we have to be very careful because of what discussed last time. This should be the spectrum of long strings. So that's what this star was there for. Okay. What else can we do to seek evidence for the correspondence? We can look at the thermodynamics. So I'm going to do this rather quickly. So the TST backgrounds that I described have a horizon, and the location of this horizon is the same as before the deformation. Since the low energy effective theory is just supergravity, you know that the entropy is going to be given by the area in Planck units. And you can compute this entropy, and it's given by this expression. What's interesting about this is that using the holographic dictionary, you can show that this is just this. And it matches the entropy that we found in the single trace TTbar case. And in addition, you can check that this is consistent with the first law of thermodynamics because you can compute this temperature. For example, by going to Euclidean signature and then trying to find the thermal circle that removes all possible conical singularities. And this temperature is given in this way. And there's a similar expression for the right moving temperature where you exchange U with V. Okay, so let me now give you some additional comments and conclusions. The first comment is to stress that the matching of the spectrum with single trace TTbar is consistent with the fact that the lone string sector of this theory of string theory in ADS3 is captured by a symmetric orbifold. However, there's a small puzzle because the entropy also matches the formula that we got from the symmetric product. And this is a bit puzzling for 2 reasons. The first reason is that, as we said in the previous lecture, the full holographic dual of string theory and ADS3 is not expected to be a symmetric orbifold. And the second puzzle is that the entropy is not expected to come from a set of continuous states, which is what the long string sector describes. But there's a tentative answer that I can provide about this puzzle. And for this, we have to know that the derivation of the entropy from the single trace version of TTbar relied only on 2 facts. At least in the way that I presented it in these lectures, it relied only on 2 facts. The first one was molar invariance, and the second one was the energies of the vacuum. So the tentative answer that I wanted to give you, that it's somewhere hidden here, is that we can make sense of the fact that we can also match the entropy to the single trace version of TTbar if the marginal deformation that takes us away from the symmetric orbifold point preserves both molar invariance and the energies of the vacuum. Okay, so we can require this marginal deformation to satisfy these 2 properties. And in fact, I can provide some evidence that this interpretation does make sense. And this comes from computing the gravitational energy of the ground state geometry. So in this case, you find that the angular momentum is 0, and the energy or the mass of the spacetime is given by this formula, which using the holographic dictionary is exactly the same formula Yeah, so the same formula used in the derivation of the entropy in the single trace case. Okay. Okay, so and to conclude, let me just say that I have provided, and I hope I have convinced you that we have several pieces of evidence that these Tsc transform backgrounds are related to single trace TTbar deformed CFTs. And the next obvious thing to try to do is to take the limit when k goes to 1 and to check if we can prove this correspondence exactly in the way that it has been done to in the purely ADS3 case, in the undeformed case. And if so, then we might be able to, for example, have at least perturbative hints of what this marginal operator has to be that takes us away from the symmetric orbifold point, and whether it satisfies the conditions that are conjectured up here, namely modular invariance, and whether it leaves the energies of the vacuum unchanged. Okay, that's it for me. Please let me know if you have any questions.
Thank you, Luis. Thank you for your 3 talks. Now, questions?